Hi guys, welcome to lecture number 8 of operating system course. We are going to talk about memory management in operating systems today. This is in your book chapter number 8 and chapter number 9. I have made a very slight change in the course flow. Previously in week 9 we were discussing mass storage structure, but in week 9 now we'll talk more about memory management, because this week we are going to talk about memory management, but it's a very comprehensive topic. I didn't want to make a very long video of 3 hours and incorporate all the details in one lecture for memory management. So I split that into two different lectures. So we're going to talk about memory management and operating system today as well, and then we're going to talk about memory management in a little bit more detail in the next week as well. So this is just a slight change in your course flow. I'm going to upload this updated course flow on Blackboard as well, so that you can refer it back. So after that we're going to talk about mass storage and file system, and finally we're going to talk about security and protection of operating system. So I have already provided you assignment number 2. We already discussed about that in the last lecture as well. So you do have time to submit your assignment number 2, so please go ahead, work on your assignment 2. It's about dining philosopher problems, and it's an essay assignment, a report that you have to write. So we have discussed in quite a lot of detail about this assignment. So if you have any questions, please get back to me, and we can talk about this in a little bit more detail. So we are approaching our project as well. So as you can see, the project is in week 8. So the allotment of project is in week 8. But what we're gonna do is we're gonna move this project to week number 9 as well, since we have moved our assignment from week number 6 to week number 7. I want to give you a little bit more time to complete your assignment first, and then you can dive into your project. Also for this project, since there are going to be a couple of projects from memory management, I want to complete this memory management portion as well before we actually talk about the projects. So let's finish this memory management part and you get done with your assignment, and then we can talk about the project in the coming week. Then we have one more assignment left, which we will talk about in week number 10 or maybe week number 11. We'll talk about that over there. So the rest of the things in the course flow, they are similar. There is no change. So these are your assessments. We are left with only one assignment after the assignment number 2, and then we have one project and the final exam. So as for the final exam, you might have received the information on the final exam. So the date has already been decided for your final exam for this course. You can have a look at that. If you have any questions regarding that, you can ask. And once I have more information on the final exam, I'll discuss that with you as well. So this is for the course flow. This is for your assessments. Let's get started with our lecture of today, which is memory management and operating system. It's a very important topic, just like process management. So we have talked a lot about processes, threads, how processes are scheduled, how processes are synchronized. We talked about deadlock, how those problems are solved. So we're going to talk about memory management now. We are going to move out of our process management and going to talk about memory management and how operating system manages the memory. When we are talking about memory, we are mostly talking about RAM, but in some cases we are going to talk about disk as well. So if you remember, we saw this diagram in our first lecture as well. So memory has different types. One of the fastest memory is the registers. Some of the registers are also part of the CPU itself. So CPU can directly access the registers. Then we have cache as well. So cache is also pretty fast. It's again a hardware device that is between the CPU and the main memory. So cache is pretty fast as well, and CPU can access cache and registers. Then we have main memory, which is your RAM. So RAM is also pretty fast, and it is used to execute your programs. So we know that any active program in the memory is called a process, and each process has at least one thread. We have talked about all these processes and threads in great detail. So CPU can directly interact with your main memory. Then we have magnetic disk, your hard drives. Then we have magnetic tapes as well. So these are the slowest ones, and these are the fastest ones. So CPU can directly interact with your RAM, with your main memory, cache and registers. CPU cannot directly interact with your hard drives, and it does make sense because hard drives are pretty slow. and CPU is very fast. So if there is an interaction between a CPU and your hard drive, this interaction is going to be very slow, and CPU will be waiting for a lot of time, which will waste a lot of time for the CPU and ultimately result in less efficient tasks. However, main memories are pretty fast. They are not as fast as CPU, but at least they can try to cope with the speed of the CPU. Cache and registers are pretty fast, so they can help CPU do efficient tasks as well. So this is the hierarchy, and most of the time we are going to deal with RAM. We are going to talk about registers as well, and we are going to slightly talk about magnetic disk as well. So this is how the hierarchy of memory looks like, and in operating system there is a memory manager that takes care of this hierarchy and when to access which part of the memory. So all of them are memories. Which memory should be accessed at what time, what would be that scenario. So that is being decided by the memory manager. That is part of the operating system. So memory management is just one component of the operating system, and it keeps track of the memory allotment. So maybe some of the files are in the main memory, some of the files are on the hard drive. Who is taking care of all these things, who is keeping the record of all these things, is the memory manager. So let's talk about memory address space first of all. And if you remember, we talked about our RAM. So our RAM looks something like this, or our main memory looks something like this. So there are some addresses. I'm giving very simple addresses. Normally the memory addresses are not like this. They are very complex. They are in hexadecimal, but just for the sake of simplicity, I'm trying to explain over here what a main memory or a RAM looks like. So this is our RAM or main memory. This is how it looks like. Obviously this RAM has been divided into different memory addresses, right? Memory addresses are based on the locations in the RAM. Now first thing to note over here is why it is risky to allow. Now before I go over there, we know that there are user processes and then there are kernel processes, if you remember. So kernel can directly interact with hardware. So RAM is a hardware, and user processes cannot interact directly with the hardware. They need to interact with the kernel space programs, and then they can interact with the hardware as well. Now why, if we talk a little bit more about why this is very important in case of RAM, why user processes should not be allowed to interact with RAM, is what if there is some data in this portion of the RAM and user process comes and removes this data, and this data, for example, is very important for the operating system to work. And if this data is not there and operating system is looking for this data, then operating system won't be able to work properly. So it's very important that user processes should not given direct access to memory addresses or to RAM in general, because of one thing, it can destroy your hardware. So some user process or some program or a virus can come and destroy your hardware. You might have heard about the cases that sometimes viruses or Trojan horses, they come and they kill your operating system, so they crash your operating system. So operating system is still a software, you can reinstall that, but what if your hardware crashes? Then hardware is expensive, so if it crashes it might create a lot of problems. So in case of software you can reinstall that, but this problem of damaging your hardware would be exponential in case of prices. So user programs can destroy your hardware. That's why they should not be allowed direct access to the hardware, in this case to the RAM. User process can crash operating system. We know that, as I just told you that in yes, sometimes hardware is very important to protect, but yes, sometimes, in most of the cases and in modern operating system, it's very important to keep good care of the operating system also, because operating system in turn taking care of everything. So as I said earlier, if some files are required by operating system and those files are being removed by a user process, then operating system would not be able to perform properly and it might crash. So it's very important that operating system is kept safe, and one way of saving the operating system is to not allow user processes to directly access the RAM or the memory. Then as I said, this one is quite related to this one. Now what if a user program comes? So for example, there is a data for Microsoft Word, you have saved a document over here. I mean, you are working on a Word document, and you want to print now. So after printing, a user program comes and remove this program, and you have not saved your work, for example, and another user program comes and remove this document from the RAM. So your word process or your word program might close. So what's happening over here is user program or user process is coming directly to the RAM and interacting with any address space that is available in the RAM, and killing the processes or removing files from it. Now in that case, you might have not saved your document and word program has closed, so you have lost changes, whatever changes you have made since the last save. So this is another problem that user programs can create, or user processes can create, if they have direct access to memory. Now this is one of the reasons, I mean, why we need to have address spaces. By address spaces I mean, so this is the RAM in journal. It has, right now it has no address space. Address space means it has not been divided into different portions. So we have a RAM and it has nothing inside, right? I mean, it has no address spaces. So over I have over this on this figure I have an address space which is 0, so address space which is 1, and so on. So my RAM in this case is divided into different address spaces, so different portions or different sectors or different sections, right? Over here if you see, there is nothing available over here, right? So there is nothing available over here, there is no address space. Now why do we need to have address spaces in our RAM? So in order to have address spaces, I mean, in order to run multiple programs as mentioned over here, so for example I have program number 1 or process number 1, it's over here, right? I need to put another process which is process 2. I might put it over here, and process number 3 over here. Now if operating system wants to access process number 2 or program number 2 or program number 1, how would operating system know in the RAM that this program is starting from this location, this program is starting from this location, this program is starting from this location? There is no way operating system can know it if there are no address spaces, right? If there are no address spaces, there is no way operating system can know where a process or a program is starting in the RAM, right? However, if we have address spaces like this, we can say that process 1 is in address space 3, process 2 is in address space 4, and similarly process 3 in address space 2, right? Operating system can come and access those address spaces, and I will tell you how operating system would know that where this process, program or process is starting. But at least having these address spaces, we can segregate between different processes. We know that in this address space this process is residing, in this address space this process is running, right? However, if we don't have any address spaces, it becomes very difficult for an operating system to know where the process is starting. So that's why having address spaces, memory address spaces in your RAM is very, very important, right? So the next thing we have to do over here is to understand how to allow different programs to interact with each other, right? So we have seen that different processes or different threads or different programs, they can interact with each other, right? So, and you have seen that for inter-process communication, we use different mechanism like message sharing or memory sharing, message passing or memory sharing. So we have seen that in our inter-process communication, and this is all what I have just told you, that it is important. So for example, if I have a RAM over here, and we have different address spaces, so this is 0, this is 1, this is 2, this is 3. Process number 1 for example is here, process number 2 is over here. Now process number 1 cannot access the address space of process number 2. This is not allowed by default. If you remember, we discussed this in process management as well. So they cannot access the address spaces of each other unless and until operating system allows them. And what is the scenario in which operating system can allow process 1 to access process 2's address space? When they need inter-process communication, when they want to access information, when they want to share information with each other. In that case, process 1 can access the shared memory of process 2. In that case, this can occur. But in traditional way, in journal, processes are separated in such a way that they are not allowed to access the address space or memory space or address space, but since they are mentioned by the addresses, they are also called address spaces. So processes are not allowed to access the address spaces of each other unless and until operating system allows them to do a certain task, to perform certain tasks, just like inter-process communication, right? So this is called address space notion. This is called memory address spaces. I hope you guys understand what an address space is and why this notion or address space is important in our memory. Now, how does operating system know where a process is starting and where this process is ending? How would an operating system know what is the size of that process? And how would operating system know that another process is starting after this address? So for example, if this is our RAM, this is our main memory, and this is the address space of our main memory. Now this is 0, this is 1, 2 and 3 and so on. So if process 1 is over here, and this is process number 2, how would operating system know that process 1 is starting from here and ending here, and process 2 is starting from here and ending over here, right? So there has to be some mechanism for operating system to know where these processes are starting, what is their length, and where these processes are ending. So in order for operating system to know that, how the processes are placed inside the main memory, operating system uses two registers. They are called base and limit registers. I will explain this to you with an example, with the diagram over here. So this is our RAM, and operating system is residing in the RAM. Obviously, if operating system has to run, it has to be in the main memory, right? So from 0 to some addresses in the memory, these are the memory addresses. These are the memory addresses. So from 0 to some portion, maybe for up till here, operating system is occupying this space in the RAM, which means that operating system has taken this space. This space cannot be taken by any other process, right? And this is maybe a free space. This is let's say process number 1, this is process number 2, and this is process number 3. This is a RAM, right? Now how would operating system know that which space has been taken by operating system itself, how much space is taken by process number 1, process number 2, process number 3, and what is the free space, right? Now operating system knows all this information using two registers called base and limit registers. These are hardware. These are the hardware that's what I said, that we are going to talk about registers, which is also a part of a memory. It's not a part of RAM, but it is a different part of the memory, which is called register, and it uses two registers. So operating system uses two registers, base register and the limit register, to know where these processes are. So in order for operating system to know what is the size of process 2, for example, it will store the starting address of the process in base register, right? It will store the starting address of the base. As I said, that these are the memory addresses. These are all memory addresses. Since process 2 is starting from this memory address, this memory address for process 2 will be stored in base register 03340. So this is the memory address which is stored in the base register, right? And the other register called the limit register will contain the length or the size of this process. So the size of this process is 120900. Maybe this can be KB or maybe bytes, I don't know. Just for the sake of understanding, it can be bytes, it can be kilobytes, it can be megabytes, or so on. So process 2 is starting from this address, and the starting address is saved in the base register. The size or the length of this process, total size of the process, is stored in the limit register. By knowing these two things, operating system can easily understand where this process is starting and where this process is ending. Now we know where it is starting, fine, but how would operating system know where is it ending? Because we know the size of this process. If we add these two, we can get the end address of the process, right? So I know, let's say for example, if I have something like this, so this is 0, maybe 5, 10 and so on. Now if I say that my process is over here, and this is my process, and the base register contains the address, starting address of this process, which is 5, and limit register contains the length of this register as well. Let's assume the length of this register is also 5. Now I would know that the length of this register is 5 and the starting address of this register is 10, which means that and the starting address is 5 and the limit or the length of this register is 5. I would know that the end address of this process would be 10, right? Which means that these two spaces have been taken up by the process, right? So operating system would know that process 1 is starting at 5 and ending at 10 because these are the values in the base and limit register. So this is how operating system takes care of the memory addresses, and this is how operating system knows where process 1 is starting, where process 2 is starting, where process 3 is starting, and what is the free space. Now we're going to talk about them in a little bit more detail. We go into more depth about what these addresses are, how these processes are stored over here. But just to give you an understanding of how operating system knows where a process is starting, where a process is ending, it uses two important registers which are called base and limit registers. And as I said, CPU has access to the registers, right? And CPU has access to the main memory as well. So CPU can always go and read the information from these registers, and pick up the process from there to process it, right? So if CPU wants to process this, CPU would know where in RAM this process is available. So it would go to base register, it will go to limit register, and would know that process 2 is over here and pick this process and start processing it, right? So this is how CPU works to access base and limit register and to pick up a process and start processing it. I hope you understand what a base and a limit register is. Now let's talk about the allocations in main memory, how memory is allocated to different processes in our RAM or in main memory. So there is a contiguous allocation and there is one more called a non-contiguous allocation. Let's talk about contiguous allocation first. Now as I said that in our RAM, our processes are allocated based on the addresses, right? So we say that memory has already RAM or main memory has already been allocated different addresses. So 0, 1, 2, 3, something like this. They have been allocated over here. Now let's assume that each portion is 2 KB, right? So each portion is 2 KB. So in that case, let's forget about this for now. So each portion is 2 KB. So the size of this one is 2 KB, size of this one is 2 KB, which means that the size is this 4, 2, 4, 6, and 8, something like this. So size of each space in each section or each space in the RAM is 2 KB, right? And we have a process P1, for example, right? And the size of process 1 is 2 KB, and we want to process it. Right, we want to process it. So what we can do is, assuming that these are all free spaces right now, there are no other processes over here. So assuming the size of the process is 2 KB, we can place this process P1 in any of these slots, so assuming these are all free spaces. Since the size of this process is 2 KB and the size of each block of memory is 2 KB, we can place it over here, no worries, right? We can do that. So this means that we need to have a contiguous free location to place our process in the memory. So this space was free, 2 KB was free, this 2 KB was free, although we had free spaces over here. And we can say that since our free space is over here, and based on the size of the process, we can place this process over here in this location, which means that we have to place the whole process P1 into this free space. Now let's assume that we have some other processes also, P2, P3 and P4, and let's assume that this is the free space available. Of course, since we said that all of the blocks are 2 KB, so let's assume this is also 2 KB, right? And we have another process P5, for example. The size of this process is, let's assume 4 KB, right? Now we cannot place this process into our RAM because the total free space we have right now is only 2 KB. Only 2 KB, right? But this process has total size of 4 KB. Since the size of the process is greater than the available space in the RAM, we cannot run this process. We have to wait for another process to complete so that we have 2 plus 2, 4 KB space, and then we can place this P5 over here. But don't worry about placing these processes for now. I just wanted to tell you what the contiguous locations are, right? So contiguous location means that a process, the space of the process or the size of the process has to be less than the available space in the RAM, only then it can work, right? Now these two spaces, since these two are now free, we can place P5 over here, 2 KB here, 2 KB here, right? But what if we have, let's assume that P4 is still executing and we have P3 which has completed. So we have 2 KB here, so we have 2 KB here and we have 2 KB here free space. We can still not place this P5 over here because there is no contiguous free location available. There is some space available here, free space available here, some free space available over here, but P5 cannot be placed over here, right? Because they are not next to each other, right? So which means that there is no contiguous free location available to place P5. This is called a contiguous memory allocation. So we have to allocate the memory to the processes in such a way they are contiguous in nature, they are next to each other. Otherwise we won't be able to place our processes, right? And we are going to talk about non-contiguous allocation in a while. I'm sure you might have already understood what a non-contiguous allocation is, but before we actually move to non-contiguous allocation, we need to see how contiguous allocation works, how we specify process memory to our processes using contiguous allocation. So I hope you guys understand what a contiguous allocation is, and I want to move forward a little bit. Now as I mentioned that contiguous memory allocation, and we are going to talk about contiguous allocation for coming few slides, and there are two ways of having our memory allocated to processes. One of the ways is, as I said, that let's have 2 KB for each block, and this is normally called a fixed size. So in fixed size, what we normally do is we divide our memory into fixed size address spaces. So this is 2 KB, this is 2 KB, this is 2 KB, or this, I'm just saying it can be MBs, it can be 10 MB, it can be so on, but for now, just for the sake of example, let's call this 2 KB. So each memory space has 2 KB over here, right? And this, if we divide our memory in address spaces of 2 KB or fixed sizes, we normally call this concept a fixed size address space. All right, fixed size address space, just what I mentioned over here in the diagram as well. So if I divide my memory into 64 bytes, and my whole memory will have portions like this for 64 KB or 64 bytes. So if a process that P1 comes which has 64 bytes, I can place it over here, no problem, assuming that this is not 2 KB anymore, this is 64 bytes, each space is 64 bytes, so we can place it over here. So if this is process 1, this is process 2, this is process 3, and this is process 4. If my next process comes which has 128 bytes of size, so if process 5 has 128 bytes of size, I cannot place it in the memory because there is not enough space, right? There is not enough space available over here. So it's very important to note over here that not all processes are going to have same size, right? Microsoft Word process, for example, might have 64 byte size. There is a Notepad process which might have only 28 bytes, right? So if it's 24 byte size, we can place it over here in the RAM. If it's 28, we can still place it, no problem. But let's see what is going to happen, right? Let's see what is going to happen. So let's assume we have our RAM and we have fixed spaces over here, and based on the same example, let's say the spaces are 64 bytes in size. All of them are 64 byte in size. So Microsoft Word process came and we have free space, all of them are free spaces. So we place process 1, let's call it process 1 for Microsoft Word. Process 1 is placed over here, no worries. Then Notepad process came, we call it process number 2. This is also 64 bytes. So what happens over here is this is a free space. Since it's big enough to hold this process, we place process 2 over here. But what happens now is some of the space over here is left empty, right? So process number 2 takes 28 bytes, for example, and rest of the space, for example, maybe 38 bytes or something, whatever this calculation is left free over here. This is left free over here. Now if a process comes if a process comes, now let's assume that maybe this is also filled by process number 3, this is filled by process number 4, this is filled by process number 5, and another process comes, let's say maybe a process comes for Photoshop, which is looking for 30 bytes. We cannot place it over here. We cannot place it over here because we do not have enough space, right? Now, although we have all the fixed sizes, this space is now going wasted. This space is now going wasted because it's part of the address space and we cannot place any process over here. Now, let's assume another process comes. Let's call this process, whatever process, let's call this process P6. Now, let's assume this free space over here, which was left by process 2. Let's assume this is maybe 36 KB, and this is free space is 36 KB. Now we have, or let's take the Photoshop process. We take Photoshop process, which is 30 KB or 30 bytes, since we are talking about bytes over here. So let's assume that Photoshop process comes and it needs 30 bytes. We cannot, although we have space over here, free space over here of 36 bytes, we cannot place it over here because it does not fall in a separate address space. This is part of this address space, right? This is part of this address space. This is not a part of a separate address space, so we cannot consider this free space as a separate address space. So we cannot place anything over here because this address space is a part of this address space. This free allocation or free memory is part of this allocation space. So we cannot provide this free space to this process, although the space available and the space required by this process is still accommodatable. We can still accommodate over here, but this belongs to a different address space, and one process is already in that address space. We cannot place it over here. This is what is the problem with fixed size, right? This is the problem with the fixed size. They all have the same fixed size. So if a small process comes, we still have to accommodate that into the address space of 64. So even if 28 is coming, we are placing it here into 64. Even if 30 is coming, we are placing it into this space. So a lot of space is being wasted. Lot of space is being wasted over here because they are in the address space and they cannot be used by another process. So what can be a good alternate to that? Now, before we go to the alternate, let's talk about another topic, which is called a fragmentation, right? If you have used Windows 98, I don't know, maybe I am too old, but I have used Windows 98, and there was a concept of fragmentation over there, which was a software, built-in utility in Windows 98. You run that fragmentation, what it does is normally makes your computer faster, and we're going to see how it makes faster, right? And it allows more processes to go in the RAM. So we're going to talk about that. So what fragmentation is, we have already discussed, to be honest, what fragmentation is, but there are two types of fragmentation. One is called the external fragmentation and the other one is called the internal fragmentation. So let's talk about external fragmentation. Total memory space exists to satisfy a request, but it is not contiguous, which means that, let me quickly draw it over here since it was a lot of mess over there. So let's assume we have some space over here. So we have a process P1 over here, P2 over here, then we have a process 3 over here, right? And let's assume that all of them are fixed sizes, so 2 KB, 2 KB, 2 KB and 2 KB, right? Now process 4 comes, the size of the process 4 is 4 KB. Now we do have 4 KB available, 2 KB here and 2 KB here, right? Although we do have, what is the total free space in this RAM? Total free space is 2 KB. 4 KB. Yes, 2 KB here and 2 KB here. But we cannot place a process with 4 KB of size, which is process number 4 over here, right? Why? Because the locations are not next to each other. They are not contiguous. If a situation like this happens where we do have enough free space to accommodate a process, but they are in different locations, they are not contiguous, we call this problem an external fragmentation. This is an example of an external fragmentation. Now again, so a concept in which we have free space, enough free space available to accommodate a process, but those free spaces are not next to each other, they are not contiguous. This problem is called an external fragmentation. This is called an external fragmentation. I hope you understand what this is. It's a simple concept. Just just that a process is not able to be processed, although free space is available in the RAM. And these are all RAM, by the way, it's not hard drive, so we are always talking about RAM. And process, although the process is requiring that much space, and we do have that much total space in the RAM, but we cannot place this because it's not contiguous. Let's talk about internal fragmentation. Now, there is a very slight difference between internal fragmentation and external fragmentation. Let's talk about what internal fragmentation is. Now, as mentioned over here, the allocated memory may be slightly larger than the request memory. This size difference is memory internal to a partition but not being used. You know, as we already discussed this, so let me do it once more. So what is happening is we have again fixed size. So I'm talking about fixed size right now. So this is 2 KB, this is 2 KB, this is 2 KB, and this is 2 KB. Now let's assume there is a process P1 comes up, and process 1 needs space of 1 KB. So we can place it over here since this is free space. Now this space has to be divided into free space and allocated space, right? So 1 KB is being used by process 1 and 1 KB over here is free, right? Now the problem over here, as I mentioned, this is part of one address space. This is part of one address space. Half of that address space is occupied by process 1 and half of that address space is still free, right? Now let's assume the others are filled, P3 and P4, right? And we have another process P5 coming up, which is 1 KB. Now we do have enough space available over here. We do have enough space available over here, but this is part of an address space where P1 is already working. So we cannot accommodate this space to P5. Now this space is being wasted. Because this is part of one address space and that address space cannot be taken by multiple processes, right? This concept is called an internal fragmentation. And the difference between internal and external fragmentation, I hope it is clear now. In external fragmentation, we do have enough space, but that is not contiguous. They are in different memory locations. Although we do have enough memory space to accommodate a process, we cannot accommodate that because they are not next to each other, they are not contiguous. In internal fragmentation, what is happening is we have enough space, but that is in a different address space or in an address space that is being already used by another process. So that space cannot be allocated to any other process now and is being wasted, right? This is being wasted. Now if we see this internal fragmentation, I think we can solve this problem by not making it fixed size, right? We can fix it by not making it fixed size. So what we do, we use a variable size, right? So we can use our RAM like this. So some of the address spaces, they are 4 KB, some of 2 KB, some of them are 4 KB, some of them maybe 8 KB, some of them 10 KB, and some of them 20 KB, right? So variable space, not fixed size, different size memory spaces. So there is a process P1 coming up and it has a size of 3 KB, for example. We can place it over here in 4, right? 3 KB. No problem. We can put it over here. If a process 2 comes which has 10 KB, we can place it in 10 KB. Over here, process 2 can go over here. But again, there is a slight problem, which is there is still some space being wasted, right? But at least it is better than the previous one. At least this process doesn't have to wait for the space to become free, right? So variable size address spaces, they solve internal fragmentation to an extent, which is still very efficient, that at least some processes, they don't have to wait. So for example, P1 has to wait in this case, but now if P1 comes over here, it can be placed in any of these because there are variable size. So there is a chance that P5 might get a space somewhere here, right? Yes, there is still some problem based on this, which is one of the problems in contiguous memory locations. We can solve this problem using non-contiguous memory location, and you will see that. But at least the problem of internal fragmentation is somewhat solved using variable sizes. At least the sizes are not same, they are different, so processes can be placed in different sizes. Less wastage of space maybe as compared to internal fragmentation, as compared to this example. Less space wastage, variable spaces, variable sizes have less memory wastage problem. So it solves internal fragmentation problem to some extent. Not 100% solved, but at least solved to some extent. So these are contiguous memory locations, and these are the ways of dividing memory address spaces using fixed sizes and variable sizes. I hope you guys understand what is going on over here, because we are going to build on this the uh, the solution for external fragmentation, which is this one, and what non-contiguous memory locations are. And it's a very important concept in operating system. We are going to talk about that in a while. So I hope you guys understand. And this variable space, one of the advantages of this variable space is it can grow, right? It can still grow. So if you have very different variable sizes, it can still grow. The processes can still grow, and they have some room to grow over here, right? I mean, that has some advantage over here also, but then the problem is variable sizes have more spaces to grow, right? So as I said, that fragmentation has two problems: internal fragmentation and external fragmentation, and we talked about them. One of the solutions to solve fragmentation is, so if I talk about this again, so we can solve for example the problem of fragmentation by compacting them, right? So we have some free spaces. So this is a free space and this is a free space. We can solve this problem by combining these two free spaces and creating extra space. So this is 2 kb, this is 2 kb, so this free space becomes 4 kb, right? So if this is occupied by P1, P2 and P3, we still have 2 slots available, and if a process P4 comes that has size 3 kb, we can still place it over here. By combining both of them and then giving it a space, we still waste 1 kb over here, which is fine. At least this process doesn't have to wait for its run. It can still go in the RAM, and although the memory space is being wasted, but at least it can go and work, right? So one of the ways of solving fragmentation is by compaction, by combining both of these address spaces and giving their space to another process, right? If we keep these address spaces separate and we don't have a mechanism to combine them, then this P4 might have to wait unless one of the processes is done, right? Now one of the problems of compaction, combining these two spaces, is CPU has to wait, right? CPU has to wait. Now let's assume a process P4 comes that needs 3 kb of space. We have 2 kb and 2 kb. Before P4 is being assigned this space, these two spaces need to be combined together to make 4 space, which will take some time by the operating system to combine them. By that time, operating system is just waiting, doing nothing, right? So the time of CPU is just wasted. So compaction, it's not very easy to do. This is the problem. This is not very easy to do. It needs extra calculation. It wastes a lot of CPU time. So imagine you have different multiple spaces. I'm just giving you a very simple example, but address spaces are very complex, right? Very complex address spaces, and these spaces might be not only 2, there can be hundreds of spaces, and the size can be more than 100. So you might have to combine hundreds of spaces to allocate that space to a process. In that case, CPU will keep on waiting, which is not at all what we want. We don't want our CPU to waste its time. This wait time might be given to some other process doing some other task, right? So one of the problems in fragmentation, one of the problems in compaction is that it wastes CPU time by wasting for these address spaces to be compacted, to be combined together, right? So this is one of the problems. Now let's talk about swapping. Now we know that RAM has a limited space. So for example, this is our RAM. For example, it has 16 kb of space. We now have 16 GB of spaces also, but let's, for the sake of this example, so you have some address space over here, and let's assume right now there is no process in here, and a process P1 comes up. And where are these processes are, by the way, coming from? They're coming from hard drive, right? So let me call it HDD, hard drive. They are coming from hard drives, right? So these processes are coming from where? Into the memory. They are coming from the hard drive. Why from hard drive? Because hard drive is containing all the programs, right? All the programs are in the hard drive, right? So your Microsoft Word, Notepad, they are all in the hard drive. So they are stored in the hard drive. Whenever we double click our icon, one of the first processes of that program will go into the RAM. So maybe this is that first process. It will go into the RAM and start executing itself, right? So let's assume we have a RAM of 16 KB and our process, one of our processes, is of total size of 24 KB. Total size of this process is 24 KB, but unfortunately the size of our RAM is less than the size of our process. So which means that it can never run. It can never run, right? It won't be able to run at all. Now that's something that we don't want, right? So it might happen that something like this can happen, because even in today's scenarios, what happens is, although our RAMs are pretty heavy these days, I mean they are 16 GB or so on, but operating system takes a lot of space in your RAM, right? Because it has to run as well, right? So some of the space is taken by operating system, which space will not be counted for the processes. So the rest of the space, remaining space, will be counted for the processes. Let's assume that this process is rest of the space, RAM space is, for example, 20 KB. This process would still not be accommodated over here, because this process is bigger than the size of the RAM, right? So what do we do in that case? We don't place everything inside the RAM. We don't place everything inside the RAM. This is what we do. We place only few processes in the RAM. Only the required processes in the RAM. Rest of the processes, they will remain inside our hard drive, right? So we place only few processes in the RAM so that other processes can get a chance to move to RAM. Now we will talk about this situation in a little bit while, where the size of the process is bigger than the size of the RAM. In that case, what do we do, right? We'll talk about that in a while. But in order to solve a portion of this problem, what we can do is, let me draw it again over here. So for example, operating system is taking some space. Total size of your, let's call it maybe 32 KB. This is the total size of your RAM. Out of this 32 KB, 12 KB, let's make it easy. 12 KB is taken by your operating system. Rest of the space is only 20 KB, right? Now in this 20 KB, there are two processes already. P1 is there, P2 is there. Let's assume they are all taking 2 KB and 2 KB. So we end up having free space of 16 KB over here. And let's assume another process P3 comes up. The P3 needs, for example, 18 KB of space, right? Now the total available space is 16 KB, so P3 has to wait. It has to wait, right? It will keep on waiting unless and until one of these processes are done. Operating system is not going to lose its space, right? Because it has to operate. So operating system has to wait for one of these processes to execute or complete execution, so that this free space can be combined together and given to process number 3, right? This is what we know. Now if the priority of this process is more than any one of these processes, operating system will take one of these processes, kick it out of the RAM and place this process P3 somewhere, right? This can be done, right? But that's a different scenario. We are not going over there. So what we have to do is, we have to, and this is in hard drive, by the way. This process is waiting in the hard drive and wants to come to your RAM. So what happens in this case is, we have to wait for one of these processes, most probably P2, because we are talking about contiguous memory location. If P1 is done, this still has to wait, because this is a separate memory address, this is a separate memory address, and they are not contiguous to each other. So P2 has to complete for P3 to be given this space, right? So once P2 is done, this free space of 18 KB will be given to P3. That's fine, all right? So we can do that. Now that's the thing, that we don't keep all the processes in the RAM, right? What if P2 is idle? It's not doing anything. It's just in the RAM doing nothing. We don't need this process to be in the RAM, because another process is just waiting for its turn and it has to do something very important. If P2 is just staying idle over there doing nothing, so we have to kick it out and bring this process in. This process of kicking out a process and bringing another process inside your RAM is called swapping. Or just in a simple way, bringing any process inside a RAM is called swapping. Well, sometimes we call swap in and swap out, but just to make it very simple, a process that is brought into a RAM will be called a swapped in process, and a process that is kicked out of the RAM, or because it has completed its execution, or maybe because of priority, is called swapped out, right? And the whole process is called swapping. right? And this is how it works. So for example, I mean, these are different stages of your RAM, and this is based on time, right? So this is your RAM, this is free space, and this is the allocation space, and this is the space taken by the operating system. So we cannot take this space from operating system to give it to any process, right? We cannot touch this space. This is the free space where we have to accommodate the processes. So let's assume number A over here, where we have process A working in the RAM. Now process B comes up, we have free space, so we'll allocate B to process B, this space to process B as well, and assuming this is the size of the process. So we still have some space, so process C comes up, we give some space to process C as well, right? Now process A is done, so this free space, this is a free space now, right? So B and C are still working, operating system is still in the RAM because your computer is working. Now process D comes. Now the size of the process D is so much that it cannot fit here, it has to fit over here in this space, right? So process D is over here. Now by the passage of time, process B is done, this space is now free, right? And process A comes back and it's given this space. So this is called swapping, adding a process to the RAM and taking out another process when it's complete or because of maybe priority, right? So this is how swapping works in your RAM. Now we have talked about memory compaction already. I'm not going into the detail of memory compaction, but there can be multiple memory holes. These free spaces are sometimes called holes, right? Holes. They are sometimes called holes. Now how to fix these holes? We do memory compaction, right? We are not basically fixing them, we are just combining them, just like what happened over here. So process B was done, there was a free space here, and the space left by process B was combined with this free space. So we had a bigger free space and A was given this space. So this is called swapping, and this is combining the free spaces over here. It's called memory compaction. And as I said that this technique is not used too much because it uses a lot of CPU time. CPU time is wasted for just completing these, this task of combining these free spaces or holes. Okay, let's talk a little bit about how to manage the free space. So we are talking about memory compaction over here. We have talked about it. We know that we can combine different holes together to make bigger space to accommodate more processes. Now how to actually do that? This is called managing the free space. How operating system manages the free space available. Now there are two methods to do that. One is called a bitmap and the other one is called using a list. So memory management using bitmap and memory management using linked list. So let's talk about them together. So let's start talking about bitmaps first. So let's assume this is our main memory. So these are the addresses of the memory, keeping it very simple just for you to understand it properly. A, B, C, D, E, these are the processes. So these are the processes, and as we know that free spaces are called holes, so these shaded spaces are called holes. So this is our RAM. So in our RAM it starts with process A, then we have some free space, then we have process B, C, then some free space, then D, E, and then some free space, and so on. Now how does operating system know where is a free space and where is our processes, right? How does it know? How does it keep track? How does memory manager, as I said that memory manager keeps track of all the allocated spaces and free spaces, all the allocated programs and all the allocation of the disk and the RAM. So how does it do that? It uses a data structure called bitmap. And it looks something like this, right? So what's happening over here is whenever there is a process in a memory location, it will be addressed as 1, right? If there is a hole, it will be addressed as 0, right? So process, if there is a process P, that space in the memory will be 1, and if it's a hole, that space in the memory will be H, hole, all right? That will be 0, right? And this data structure called bitmaps is keeping track of all of these. So if you see, our memory addresses are starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on, right? So it's like this. So what this data structure is doing is, what is the first space? Is it occupied by a process? Yes. Address space 0, address 0 is occupied by a process. So in space of address, in the place of address 0, we'll place 1 over here. What about address 1? It is occupied by a process? Yes. If you see, the address of process 1 or process A is from 0 to 4, right? So it has total of 5 bytes, for example, right? 0 to 4. From here to here, this space in the RAM is taken by process A. So what we're going to do, in place of in place of address 0, we'll place 1 because it is occupied by the process. 1 is occupied by the process? Yes. 2 is occupied by the process? Yes. 3 is occupied by the process? Yes. So we place 1 whenever a process is occupying that space. 4 is occupied by a process? Yes. What about 5? 5 is a free space. This is 5, right? So 5 is a free space. So we replace 5 with 0. We replace 6 with 0 because it's a free space. We replace 7 with a 0. We replace 8 with 1 because this is occupied by process B. So this is 8, and 9, and so on. Now, by creating a data structure like this, operating system knows where is a free space and where is a process available. So whenever next time another process comes, operating system will go and see its data structure and see what are some locations where it can place a process. So for example, a process, let's say process F comes up, and operating system is maintaining this data structure of bitmap, and let's assume that it needs 3 bytes, right? It needs 3 bytes to complete its execution, right? So operating system will start from beginning, searching for 3 consecutive zeros. 3 consecutive 0. Why 3 consecutive 0? Assuming that each free space is 1 byte, right? 1 byte. And for F, we need 3 bytes, right? So we need 3 consecutive zeros. So it will start from beginning and start searching for 3 consecutive zeros. It will find 1 0 here, second, third. So this free space, which is this free space, it will give this space to F. Very simple, right? So it will give this free space to F, because this is how operating system knew, by knowing the zeros, that okay, this is the free space which is available at this address, and it will go over there, right? Now this data structure, now it is made over here to accommodate some space on the page as well, but this can be done in a longer bitmap like this as well. It can be done in rows and columns as well. Normally it's done in the form of rows and column because it's a matrix anyways, it's a bitmap of zeros and ones and it is done like this normally, right? So this is how an operating system manages free space and allocated space using bitmap, and bitmap is just a data structure which I have shown over here. So you can go through using a for loop, checking where is 1 and where is 0, and by this operating system would know that this is a free space available and I can accommodate a process of that much space over here, right? So this is memory management using bitmap, and in this case we are managing free space, right? We want to know where is the free space, and we can know where the processes are also by having a look at these ones, right? So this is memory management using bitmap. There is another way to manage memory, that is using linked list. I'm sure you guys have already studied data structure course and you have already gone through what a linked list is, what is an array, what is a tree, and so on. So I'm assuming that you already know what a linked list is, but just to quickly tell you, a linked list is a set of nodes that contains the address of the next node, right? Contains the address of the next node, right? So this is a linked list. This is how a linked list looks like. So if I want to so if this is node number 0, this is node number 1, this is node number 2. If I want to go to node number 1, I have to start from 0 and I'll continue moving, right? Similarly, if I have this one, node number 3 over here, if I want to go to node number 2, I have to start from the beginning as well, and then only I can go to node number 2. So I have to go through each node to reach that node, because each previous node contains the address of the next node, right? And this is normally called the head, right? It's normally called the head. This is where the linked list is starting, right? So this is how a linked list works. Now it's the same example. Forget about this for now. This is for bitmap, and this is the same. Let's assume the same example. This is our RAM. This is our main memory, where these are holes H and these are processes, right? So how linked list manages this? Now forget about this. We are not talking about bitmap anymore. We are talking about linked list. So how linked list manages that, right? Linked list manages in this form. So each node of a linked list, so this is the node of a linked list, it will start with a flag either P or H. P means a process, H means a whole. So it will start looking from beginning, from the head of the linked list. It starts from here. If it's a process, so this 0 up till 4 here, then 5 here, and so on, right? So it starts from here and sees, and so operating system will store this information in a linked list like this. So it will start from 0 and it will say, okay, from 0 is the starting point, and this is going to be the length of the process, So this first bit in the data of the linked list is either P or H. If it's a process, then it's P. If it's a whole, then it's an H, right? So since process A is a process, it's not a whole, so this first bit will be a process. So we're going to say that first node of the linked list is going to be a process. This node contains the starting address of that process, and this node contains the total size of the address, size of the process. So starting address of this process is 0, and the length of this process is 5, starting from 0 going up till 4. So the total size is 5, right? By this we can clearly see what is the ending address. We can calculate the ending address because it is going to be 0 to 4, and that is the size of 5, right? And the last link is the link to the next node. If we go next, then we'll see over here that this is a whole, right? So the next node of the linked list will have H in it because it's a whole. Where it's starting from? It's starting from 5. What is the length of this whole? Length of this or size of this whole is 3, right? And then we go next. Next, starting from 8, we have a process. 8, the size is this, and so on and so on and so on. By this, operating system now keeps track of all the processes and all the wholes, right? Now, whenever operating system wants to get back and see, and it wants to place a process somewhere, it would find easily the free, since we are managing free space, it can easily find the free space by checking a node that is having a hole in it, and then checking the size of it based on the size of a process. So just like the previous example, if F with 3 bytes, process F with 3 bytes comes in, it will go and see a hole that has size of 3. So it will check hole, and it will go and see the size of that hole. If that is equal to, if this size is greater than or equal to the size of your process, it will place it over here, right? Which is maybe to this location, right? This is how operating system keeps track of the free spaces and allocated spaces using a linked list. Now you can see over here, and I'm sure by learning the data structure course, you already know that one of the disadvantages of a linked list, as I mentioned over here, is that it has to start from head and it has to go on, carry on. You cannot just jump to any one of the nodes, right? You cannot jump to any one of the nodes. You have to start from the head always and start searching up till you go to the end. That makes this whole process a little slower, right? Because this is one of the disadvantages of having a linked list, although it has a lot of advantages, as we have seen. But the only disadvantage of memory managing using linked list is that it is a little bit slow, right? So this is these are the two processes, these are the two methods of managing free space in operating system, and this is how operating system keeps track of the free space and the allocated space. Now again, I mean, it's just a simple notation of telling what is happening over here. So what happens is, let's see, there is a process A, B and X, and this is the situation before X terminates, and this is the situation after X terminates, and these are different cases. So in case number 1, what is happening is, this is process A, this is process X, this is process B. If this is the scenario before process X terminates. If process X terminates, this is going to be the free space. Very obvious, right? This is going to be the free space, and A and B are going to be like this. What if we have a case where we have only 2 processes, A and X, and this is already a free space? Now if X terminates, this is the figure after X terminates. If X terminates, this is going to be our free space. So compaction will happen in case we need compaction, and we get a free space. And similarly, we get a free space like this, and we get a free space like this. These are very obvious diagrams, but just wanted to tell you that we are still talking about contiguous memory locations over here using linked list. Alright, so now let's talk about some algorithms of how to manage the memory space using the linked list. Now you might have noticed over here that there might be different places where we can place our process F, right? So there were free spaces here also. There was enough free space over here also. Where do we actually place? This is also a free space of 3 KB. This was also a free space for 3 KB. Where do we place this F? How does operating system know where to place this, right? And there might be other free spaces also of the same size, or maybe more size than this process requires. How does operating system decide which space to give to the process, right? And there are several algorithms for that. The first and the simplest one is the first fit algorithm. So let's see. This is our RAM. This is our RAM. This is a process. This is a whole of 25 KB. This is a process. This is a whole of 50 KB and 70 KB. Let's assume we have a process of 40 KB. Let's call this process, and this is process 3, by the way. Okay, so let's assume we have a process 4 which is 40K. The size of this process is 40 KB. What operating system does is, using the first fit algorithm, now you can see that there are two spaces which are greater than or equal to 40K. So this process can fit in this space also, and in this space also. 25 is less than 40, so this process cannot fit here for sure, but it can definitely fit in this space and this space, right? So how operating system decides which space to give to this process? Now based on the first fit algorithm, what it does is it will find the first available big enough space and place that this process over here. So it will start searching, since we are talking about linked list again, so it has to start from head, right? It will start from head, which is this part, and it search for enough available space for this process, which is 40 KB. So this is 25 KB, it will not fit here. This is 50 KB, it will just place this process over here. So process P4 will be allocated over here, and there will be 10 KB of free space, right? 10 KB of free space, because there is 40 out of 50 will be 10 KB of free space. So this is what is happening over here is, this process will be divided, this whole will be divided into the process space, which is 40K, and unused memory or free space, or a whole, which is of 10 KB, right? So based on this algorithm, what happens is, it starts from the beginning, whatever first space, enough space it finds to fit that process, it will place it over here. It will not go and place it over here. This is the first place it found the enough space, and it will place it over here. That's it, right? So this is called the first fit algorithm, and it is considered quite fast, right? Because it will just go and place and not search for all the free available spaces. It will go and find the first enough space available and place that process over there. So this is called the first fit algorithm for managing memory using linked lists. The other one is next fit algorithm. Next fit algorithm. So what happens in next fit algorithm is, for example, let's use the same example. P4 has P3 or P4. P4 has 40 KB of space required, and our head is over here, right? Our head is over here. So it will find, now using the next fit algorithm, as what is happening is, let's assume that this algorithm has never run before, right? This algorithm has never run before, which means that our head will be here, right? Our head will be here. It will start from the first location, and it will search for the available space where it can accommodate 40 KB, right? Can it accommodate over here? No. Can it accommodate over here? Yes. So what it will do is, it will just replace this with P4, right? And it will have a free space H or whole of 10K over here, right? And it will keep a pointer over here as well. It will keep a pointer over here, What this pointer does is, whenever next process comes, so let's assume our P5 comes now. P5 needs 20 KB of space, right? 20 KB of space. So P5 comes. What this algorithm does is, according to this algorithm, now the operating system will not start from head. It will not start searching for free space from head. It will start from this pointer where it stopped, where the last iteration or the last search stopped. It will start from this space now and start searching for 20 KB of free space. right? So it will go and allocate the next free space is over here, 20 kb, right? So it will allocate 20 kb over here, and 50 kb will be whole, right? 50 kb of whole, right? So this is what is going to happen. If it was not next fit algorithm, what operating system would do is it will start from beginning, then find a 20 kb of hole and place it over here. But since we are talking about next fit, in the first iteration, the process was allocated a space over here. So next time, that's why it's called next fit. It will not start from the beginning. It will start from the place it was stopped and start searching for place after that, enough space for that. That's why it placed 20 kb over here, right? And obviously this is low performance than the first fit, because this was enough space over here and it did not place it over here. It just placed it somewhere here, starting from here. So it didn't do well because it didn't search this space which was enough for this, and it ended up putting this into 70k. If it place it into 20k, less wastage of space, but in this case it's a high wastage of space, right? So this is called next fit algorithm, and it has less performance than the first fit algorithm. Now the best fit algorithm. Best fit algorithm, what it does is it will find the hole that is best fit for this particular space. So for example, we are looking for 20k. So a process P4 is of size 20k, and what operating system does in case of best fit, it will scan through. Of course it will start from head because it's a linked list again. It will start from head, it will not keep a pointer. So it will start from the head and it will scan through the whole list first. It will scan through the whole list first and try to find a space where it can fit P4 and less space is wasted. Less space is wasted, right? So what it will do is it will scan through once from through all the linked list. Now operating system, after scanning through all the linked list, knows where is which free space, right? So there is 25 here, 50 here, 70 here. If this 20 is placed over here, we are left with 50k of wasted space, right? If you place it over here, we are left with 30k of wastage space, right? If we place it over here, we are left with 5k of wastage space. So best fit algorithm will place this process based on less wastage space, where it is best fit. So best fit is in this space because less space will be wasted after placing this process in this hole. So this will be 20k of the process, 20k for the process and 5k for the hole, right? So that's what best fit algorithm does. But as you might have imagined, and if you have studied data structure, you know that this will take a lot of time to do. So it has to go through all the linked list, and then it will go to the best place. So it performs slower than the first fit, right? So this is the best fit. Worst fit is contradictory to the best fit. What it does, it will go through the whole list. It will go through the whole list and find the biggest space for that process. For example, we have P4 again, and let's assume we have 20 kb again. So what it will do is it will find the largest available space. So we know that largest available space is 70k. It will place it over here, and the rest of the 50k will go wasted. That's why it's called worst fit. But why do we use it if it's worst algorithm? Why do we use it? In some cases, we have processes that keep on growing, right? They keep on growing. So in that case, if I place it over here according to best fit, then it can grow for only 5 kb, right? 20 kb for this process and 5 kb extra cushion for growing. If over here, then it might have some space for growing, but over here it has a larger space to grow, right? So in some cases it might work worst fit algorithm, but that's why it's called worst fit, because it might end up wasting a lot of space, right? So these are few of the algorithms which are for placing our processes in the free space. The last one I want to talk about is a quick fit algorithm. Now in quick fit, what happens is operating system actually maintains a list for the holes and the processes like this. It can be an array, right? It can be an array. So 0 1 2, so these are holes, and 0 1 2, these are separate arrays, right? And these are processes. So operating system, before fitting into anything, it will go and check these lists first of all, and based on these lists it will go exactly to that location, right? It will go exactly to that location and find a hole from there, right? I will leave this to you guys because I don't want to explain this and then I mean you get to see only the videos. What I want you guys to do is at least go and try to learn this quick fit algorithm. It's a very simple one. I already told you the idea of doing it, but this is how it does. I mean, it maintains different spaces, and maybe you can try to implement that. In today's lecture we are not going to do any implementation in our programming languages. What we're going to do is we're going to do a separate exercise today, and I'm going to explain you what that exercise is when we complete all the theoretical concepts. But for now, what I want you guys to do is try to learn this algorithm on your own. It's pretty simple. It's written over here as well, but try to see this algorithm on a paper with paper and a pencil, and try to debug this algorithm on your own. Draw a figure and see how you can place different processes over here. I will leave that to you guys to do some study. All right, and I'm going to move forward. We're going to talk about now virtual memory. All right, the concept of virtual memory is one of the most important topics in memory management in operating systems, and in a lot of exams, whether you go for GAT exam, whether you go for GATE exam, whether you go for GMAT, or whether you go for other entry test exams for in different universities for your master's program or a PhD program, you will find at least one question coming from virtual memory or pages, right? They will ask you some questions from this concept. So we're going to talk about this concept now, and I would love to bring one question from this concept in the final exam as well, because it's very famous and it's very, very popular, and I cannot emphasize more on the importance of this topic. So please understand this topic very, very carefully. It's a very important concept, and once you understand this concept, you will actually understand what is going on in the memory in the modern operating systems, right? You might have some idea how we are placing different programs or processes in our RAM, how they are taken out, swapped in or swapped out. You might have a little bit idea of what's going on, but this is what operating systems are doing now. Modern operating systems are using virtual memory to swap in their processes and swap out their processes. Now, up till now, what we have done is we have talked about contiguous memory locations, and we have seen the advantages and disadvantages of contiguous memory locations. So what is happening is, if this is process 1, this is some free space, this is process 2, and this is process 3, for example. Let's assume this is 2 KB of free space, this is 2 KB of free space. We have a process P4 coming up, and it needs 4 KB of space to execute, to go in the RAM. Right now, since they are not contiguous, we cannot run this program, this process or program, right? Because there is not enough space for this. But the problem is we do have enough space. We do have 4 KB free space available, but the unfortunate thing over here is it's not contiguous, and we know this is called external fragmentation. This problem is called external fragmentation, and with contiguous memory locations we cannot solve that problem. So scientists have come up with another solution to solve this problem, and that is called virtual memory or non-contiguous memory allocations, through non-contiguous memory allocations, right? And they came up with the concept of pages. Now let's talk about pages first of all. Let's understand what a page is first of all, and then we'll get back to our virtual memory. Now, the concept of paging means we divide our address space into small chunks called pages, right? Now let me explain this through this slide. Now, paging means we divide our process into small chunks of memory spaces or address spaces, right? So if our process 1 has let's assume it's 6, we have an example over here. So let's assume the size of the process is 8 bytes. So the whole size of this process is 8 bytes, and we have divided into 4 different equal parts. We divided our program, our process, into 4 equal parts. So the number of pages inside this process are 4, and each one has a size of 2 KB or 2 bytes, in this case 2 bytes, right? So what we are doing is, the concept of paging says that divide your process into small chunks of equal sizes, right, of equal sizes, and we call those equal sizes pages. So this is called, so these all are called pages. So one of these is called a page, this is a page, this is a page, and this is a page. So what is a page? Page actually is a small portion of a process. We are not talking about threads right now, we are talking about process. Now thread is a different concept, and you know what a thread is, what is the difference between a process and a thread. Now pages are totally different, right? Pages is just small chunks, similar chunks of, so for example I have let's say 0 1 2, so we have 16 lines of code, right? 16 lines of code in our C++ program. So what we're going to do is, now just to give you a simple example, this is not exactly how modern operating systems work, but just to give you some understanding of what paging is, what we're going to do is, we're going to divide our program's first 2 lines and place it into page 1, next 2 lines here, next 2 lines here, and so on and so on and so on, or maybe 4 lines, right, since there are 4 pages. So first 4 lines in page 0, second 4 lines in page 1, then in page 2, then in page 3, right? So our whole process is actually divided into different splits, into different pages, and each of these will have, well, to keep it simple, each of these pages will have a same size, right? In this case we have a process of 8 bytes. We divided it into 4 different pages, 4 different sections, and each of these section is 2 bytes. We normally call this section a page, and that's why dividing a process into different pages is called a paging process, right? A paging process. I hope you guys understand what is paging, right? Splitting a process into different pages is called paging, right? Now we got this, and how does this solve a problem of external fragmentation? How does it solve the problem of external fragmentation, and why it is so important, right? Now what happens is, when we do paging, which modern operating systems do, what operating systems do is, they divide main memory also into small sections of address spaces, and they call it a frame, right? Now address spaces are divided in, so now let's not talk about address spaces. Main memory, the whole main memory is not now divided into address spaces, it is divided into frames. So it is divided into different frames. Now the size of page and the size of frame is going to be always same, right? Now I have divided my process into different pages, and size of each page is 2 bytes, right? I'm going to divide my main memory as well into different frames, and the size of each frame will be equal to the size of the page. So if the size of my page is 2 byte, size of each frame will be 2 byte as well, right? If my memory has a total size of 16 byte, I will have 8 frames into it, because I have to divide my memory into 2 bytes of size, because the page size by the operating system is 2 bytes, right? So now what we have is, this is what is written over here, the page size will be equal to frame size. Now what we have done now is, we have taken a different approach. What we have done is, we have divided our process into different pages, into different sections, and then we have divided our main memory also into different sections, and each section is called a frame, right? Now let's see how this solves a problem. How does this solve a problem? Now okay, let me draw it over here. Based on this one, right, based on this example, we know that if we are using a contiguous memory location, we cannot accommodate this process into this memory space. Now let's assume that based on our paging concept, I'm gonna do like this. I'm gonna divide this process P4 into 2 pages of 2 KB size. So 2 KB for page 1 and 2 KB for, or let's call it page 0 and page 1, right? So I have divided my process P4, the total size of that process was 4 KB, and I have divided my process P4 into 2 pages of 2 KB size each. Why 2 KB size each? Because the size of each frame, let's assume, is 2 KB. Now what I have done is, in order to overcome this problem, is I have divided my process into pages. Now I have to divide my main memory into frames as well. So I will divide my main memory and I will keep the diagram like this to avoid more mess into it. Let's assume that I have divided my main memory into 2 KB of frames each. So this frame is taken by P2, this frame is taken by P1, this frame is taken by P3. Now how I can solve the external fragmentation page is, as you know that based on my contiguous allocation, memory allocation process, I cannot place this whole process anywhere here, right? Because they are not next to each other. Free spaces are not next to each other. Now my process is divided into 2 different pages. What I can do is I can place this page 0 into this location. So page 0 into this location, which is 2 KB, right? 2 KB. So this size was 2 KB as well. And the size of this page is 2 KB. And I place this one over here, page 1, right? I will place it over here. Now my process can easily execute, right? Because the pages are over here in this RAM. This is how we solve a problem of external fragmentation, by having enough spaces and splitting those enough spaces into frames and splitting our process into pages, and finally placing those pages into available frames like this. If you see, our problem has been solved now, right? Our problem has been solved. Now this is the abstract view or bird eye view of how paging works. I hope you guys understand what a page is, what a frame is, and how virtual memory and this whole concept, this whole broader concept of using non-contiguous memory locations, dividing main memory and processing into pages and frames, is called a virtual memory concept, right? Virtual memory concept. Now this problem has been solved, that is excellent, but it is pretty complex process. How this process is actually managed by operating system, how, okay, so we know that we have placed page 0 for process 4 here and page 1 over here. Now these are not contiguous memory location. How does operating system know that page 0 of process 4 is at frame number 2, it's at frame number 1, so 0, 1, 2, 3 and 4 is at frame number 1, and how does it know that page number 1 of process 4 is at memory location 0, 1, 2 and 3? How does operating system know that? Assuming that there is not only one process, main memory might be having several pages of several processes. How does it know that it's solving this? How does it know that the addresses are maintained? How does it know which page is at which place in the memory, right? That's a complex process. And how does operating system know that? Operating system maintains a small unit called memory management unit that takes care of this process, right? Memory management unit is actually a part of memory, and it's an intelligent unit. What it does is it maintains mapping of each process, each page, right? So what it does is it maintains a page table. It maintains a page table which contains some information like this. This is some of the many things a page table contains. I'm going to show you the other information it contains as well, but just to keep it simple and just to make you guys understand how operating system knows that which page is stored in which frame, it maintains a page table through memory management unit. So a memory management unit of an operating system or the memory maintains this page table, and it contains information of all the processes, pages, and all the frames there where there are. For example, this is if this page table, so each process will have a page table. So P4 will have this table. If there is P3, it will have another table, page table. P2 will have another page for itself, right? So each process will have a page table like this that is being maintained by MMU, memory management unit. So if operating system is looking for pages for P4, it will go to memory management unit and ask memory management unit, tell me at which place in the main memory I can go and find, for example, page 2 for process 4. It will tell that, okay, go to frame number 0 of main memory, and operating system will tell CPU what are the address spaces, how to go to those address spaces, and we have talked about that, but we are not going into the depth of address spaces right now. because we are talking about pages right now. So it will tell operating system will tell CPU, okay, frame number 0 is available, maybe for example at address space from 4 to 16. So go to that address space and you can fetch that frame from there. So this is how paging is done. This is how virtual memory works, and this is how memory management unit manages the page table for each of these available processes, right? I hope this is making sense to you. If you understand up till now, then I hope coming concepts won't be difficult for you. So this basic idea of understanding a virtual memory and paging makes, I mean, it becomes difficult for student. I don't know. I try to make it very simple for you guys by giving you very simple examples, so that you guys understand what a page is, what a frame is, what is paging concept, and what is a virtual memory concept, how memory management unit works, and so on, right? So these are the very basics of virtual memory, paging, memory management unit, frames, and pages. I hope you guys understand up till now. So this is what I actually did. Explained you in a broader sense, but let's take a little bit more depth knowledge of how this is happening, because we are going to do an exercise on that. Right now, CPU is actually containing the logical addresses. What is a logical address? A logical address is a memory address that is being generated by CPU, right? And there is another address called physical address. Physical address is the actual address in the RAM, right? So the actual address of the page in the RAM. So for example, page 0 is here, maybe this address is 54. This is called the physical address, because this is a real address of the page in the RAM, right? Now CPU also generates some logical addresses. CPU also generates some addresses. Normally you use them through pointers as well in programming languages. So those are the addresses that are being generated by the CPU. Now these logical addresses needs to be converted to physical addresses for CPU to go and fetch that information. As I mentioned earlier, the CPU doesn't know anything about where a page is residing in the RAM, right? And how does it know that? This information is provided by the operating system through MMU to the CPU, and then CPU will go and fetch that page, right? So how is this happening, right? So let's assume we have a process called, let's say P1. We have a process P1. Now process P1 will have a logical address generated by the CPU, right? So process 1 will have a logical address that is being generated by the CPU, right? Now that process will have, let's assume this process P1 that is being split into different pages, right? So process 1 is split into different pages. Let's assume it's split into 3 pages, right? Each page will have its own logical address. Each page will have its own logical address. After the process, each page will have its logical address. Let's assume that this logical address is 24, right? And it will have some offset. What is an offset? Now offset means, so for example, we have our page P0 since we are talking about P1, and let's assume this page 0 is placed somewhere in the RAM, right? Now this page 0, if we go into the detail of this page, it might have some lines over here which is C out, C in, and do something else over here, right? Now it has maybe a variable int a that has some value 5, right? And you want to access that value, and that is maybe some byte. How do I know, how do I get that information? That information is being provided through offset, right? Which line or which variable or which byte I actually want to access within this page. So basically this page will have some information like this, right? It's just bits and bytes, right? So every information in the RAM is bits and bytes. So which byte actually I want to access is through this offset. So for example, I want to access byte number 5, right? So somewhere byte number 5 I want to access. So what will happen is this information of this process, this page will go to the memory management unit, right? And memory management unit, what it will do is it will store this information in a page table. This is a page table, right? So let me put page 0 here, since we are talking about page 0. and let's talk about 0 and 1. So let's assume that page 1 is available at frame number, page 0 is available at frame number 1, which is over here. Now memory management unit maintains the page table, as I said, for each process. So for process 1 also it's maintaining this page, right? So what this memory management unit does is it will pick from here the frame number corresponding to this page 0, since we said this is page 0, and it will generate the physical address of that page through the frames, right? So it will say frame number, so this was frame number 1, for example F1, so it will do F1 and it will keep that offset as it is, number 5, right? It will keep that offset. So it has generated now for us the physical address. From the logical address, memory management unit has generated a physical address for us, right? And we know how it does it, because it is maintaining a page table that is a mapping between the page numbers and the frame numbers. So it took from here the frame number of the corresponding page, which was page 0 in this case, and it generated a physical address, which is in this case, I'm keeping it very simple, but normally it's not like this. This is in the form of bits, right? Zeros and ones, and we are going to do an exercise. You'll get to know how this works. So it will have now a physical, so we now have a physical address F15, which means that it will go to frame number 1 where this page is, and once it accesses this page, it will go into the detail of this page and pick up byte number 5 from here. Maybe this is a variable or this is a value, maybe let's say there is a value 10 over here stored, right? And CPU will use this value to make its calculation, right? So this is how this whole process works for the memory management unit. It translates the logical addresses using the page table into a physical address. This physical address is then provided to the CPU. CPU goes and accesses that information. At that information, it might have a number, it might have a byte, it might have some information, and CPU does some calculation based on that number or that value, right? This is how this whole process of memory management works using pages, right? I hope you guys understand. Try to rewind this video a couple of times and try to understand what is going on over here, and hopefully you will understand. I try to make it very simple based on these drawings. I made these drawings just to make you guys understand what's going on over here, so that you actually understand what is the process of mapping between logical addresses and physical addresses. Okay, so let's move further. Now let's further understand what's going on. Now these virtual pages, normally these are the pages, right? So these are the pages. These pages for different processes. So process 1 will have some pages, process 2 will have some pages, and so on and so on. These are actually placed inside your disk or your hard drive, right? Inside your hard drive, because RAM will only contain the pages, processes, or within processes only the pages that are required to run that program, right? It will not contain all the pages. It will contain only the pages that are required to run that program. So maybe P1 contains 3 pages, right? So let's pages PG0. So it contains PG0, PG1, and it contains PG2, right? Now process 1 contains these 2 pages. So it requires page 1 to be in RAM to start its execution. So first of all, this will go inside the RAM at some location provided by the operating system. PG0 will go in the RAM and the execution will start. And then page 2 will have some instruction to fetch page 1 as well. So page 1 will say, now I need page 1 in the RAM to continue the execution of this process. So page 1 will be brought into the RAM, right? And maybe page 2, what it does is it just clears all the RAM, all the memory, or closes the file. Maybe this page 0 or page 2 is required at the end of the execution of P1, right? So these pages are executing for 10 minutes, and in last 1 second, page 2 is required to do the cleanup, right? Or close the file and so on. So this might happen sometimes, that some of the pages are very important or very critical for the process to execute, but one of the page might be required at the end. So we don't need to bring all these 3 pages at the beginning of the execution of the process into the RAM. We don't want that, and we don't do that, right? This is not required. Whenever a page is required in the RAM, it will be fetched from the hard drive into the RAM only when it is required, right? That is called demand paging. Demand paging. So pages are brought into the RAM based on the demand, right? Now we know that RAM is quite limited, right? RAM is quite limited, so the space in the RAM will be very limited, but the space in the hard drive might be more than, it will always be more than the RAM. So the pages inside the hard drive can be many than they are in the RAM. There are so many pages in the hard drive than the pages that need to be brought into the RAM. Not all pages need to be brought into the RAM. Now which pages need to be brought into the RAM? That is very important to note, right? So these are the spaces in the hard drive. So at space, for example, at address space, now just like RAM, hard drive also has address spaces, right? Because it's a memory. If we don't know at which memory space or which memory address our information is available in the hard drive, we cannot fetch or use that information. So hard drive also has address spaces, right? So let's assume that at hard drive location this, we have some page 7 that we not need to bring it to our RAM, right? It will be fetched based on demand, and so on and so on. These X means nothing is placed. So at these location, at these address spaces, we have holes. I mean, not holes, I mean we don't have any information. And the numbers means we have some information over there, right? So just wanted to show this diagram to tell you that there is more space in hard drive to store pages, and there is less space in our RAM to store pages. So we don't bring all those pages into the RAM, we bring only the pages that are required. And this on demand paging is, and this concept of bringing the pages on demand is called on demand paging, right? So the virtual memory might have 64K space, and our RAM might have only 32. Just to tell you that the space in the RAM is less than the space in our hard drive, right? Just wanted to tell you that. Now very important concept is the page fault concept. Page fault. What is a page fault? Now page fault means if a page is not in the RAM and that is required by the CPU. For example, if CPU is looking for page number, so let's assume P4, process 1 also has a page 3 in it. So we now have page 0 of process 1 in the RAM, page 1 of process 1 in the RAM, page 2 of process 1 in the RAM. We have all these pages. Now after executing all these pages, CPU is looking for page 3 of this process. How does CPU know that there is a page 3 also? Because page 2 might have some instruction asking for page 3 as well, and MMU is also containing all the pages of the process, right? Now CPU is looking for page 3. Now it will go and search for this page in the RAM, and it will not find that. If CPU does not find a page required by the CPU to complete the execution or to process that process, that is called again. So if a CPU is looking for a page for a process in the RAM and it does not find that page in the RAM, this is called page fault. Page fault has occurred. So CPU was looking for a page inside the RAM, but it does not find that in the RAM. This is called a page fault. So a page fault has occurred, and it is very normal for page faults to occur because we cannot place all the pages for all the processes in the RAM. So it's absolutely fine to have a page fault to occur, but it's a good idea to have less page faults, right? It's a good idea to have less page faults, and we will see how we can make less page faults to occur, right? So as we said that page faults are very normal to occur in memory management, and page fault occurs when a CPU is looking for a page and that page is not in the RAM. That is called a page fault. Very simple, and this is what we are telling over here. And page fault is told by a bit called present and absent bit. I'm going to show that to you in a while where that is, but just to tell you that this is a page fault, and it occurs if CPU does not find a page inside the main memory, and it is absolutely fine to have that. And we have discussed demand paging as well. So if page fault occurs, we bring that page on demand from the disk to RAM, right? So if a page is required by the CPU and that is not in the RAM, we will request that page from the drive, right, from the hard drive, and that is called demand paging, right? So these are two important concepts. Now memory management unit manages the addresses, right? What it does is it converts the logical addresses into physical addresses, right? So it will have some logical address and it will convert that into physical address, and we are going to do an exercise on that, and I'm going to explain that to you, even this diagram during that exercise. But for now, just note that a memory management unit will convert the logical addresses into physical addresses, right? And in a logical address, normally we will have 16 bits, 12 bits for the offset, and 4 bit for the page number, and I will tell you what that is when we do an exercise. Now we have been talking about page tables, so we know that memory management unit MMU is maintaining the page table, and if you remember I showed you, so it will have mapping of page numbers to the frame numbers, but it doesn't only have the mapping of page numbers to frame numbers, it has many other things. So normally a page table looks something like this. It has a lot of other information. So it will have the page frame number, right? It will have the number of page in the, like I said, it will have that mapping for sure. Then it has a present absent bit. 1 is for valid and 0 for page fault. So if this page, so this is one page, right? So in page table, so this is my page table, right? And it will have all these fields. So it will have all these fields. So this field is caching field, maybe this is the reference field, and so on, and it will be having different entries for different pages, right? So this is for page 0, page 1, and page 2, and page 3, right? And this page table will be for each process. So for example, this is for page 4, right? This page table will be for page 4, right? So it contains the mapping, yes, and we talked about that. It contains the mapping. It contains a bit called present and absent bit, which tells that a page fault has already occurred for this page, right? So this page was being looked up by the CPU and it was not there in the RAM. So if it was not there, which means that page fault has occurred. So if page fault has occurred, we'll mention a 0 in the present absent bit, which means that 0 means it was absent and a page fault has occurred for this page already. So this will keep track of how many page faults have occurred for this specific page, how many times CPUs was looking for this page, and how many times it has been looked for, which will tell operating system that this page is being looked up many times, so better keep this page somewhere so that CPU can easily access that. And I'm going to tell you why we need that, right? But for now, this flag is normally used to indicate the page faults. If page fault is occurring, then it's 0. If there is no page fault, it's 1, right? Then a protection bit. There is a protection bit also that tells if this page is readable, writable, or executable. If there is a 0, then it's a read writable. If it's a 1, it's only read only, right? So just to get some extra information. Then modified, this bit is set to 1 if this page table has been modified. For example, this page has been modified. If this page has been modified, then this bit is 1, which is normally also called a dirty bit because it has been modified, and otherwise it will be 0. Then we have referenced, how many times this page has been referenced by CPU, right? For example, now this and this are totally different. Now this page might have been in the RAM and have been referenced by CPU many times, and this bit will tell that how many times this has been referenced and how many times this has been referenced it was not there in the RAM, right? So these are two things. And then cache is enabled for this one and not. This is a vast topic, so we are not going there, but this is how your page table looks like in your RAM. One important thing to note over here is, as I mentioned, that each page will be in the RAM. Each page will be in the RAM. So this is, for example, page 1, page 2, page 3, and page 4, right? Now MMU, memory management unit, will check the page table, right? It will check the page table to see which frame they are in, right? So these are frame numbers, right? So these are frame numbers. So memory management unit will check the page table. That will give us the mapping of where each page is mapped to a frame, right? So page 1 is in frame 0, page 2 is in frame 1, right? Now that is perfectly fine, but where does this page table reside? Where is this page table, right? This page table is also in the RAM. this page table also resides in the RAM. So it is important to note that this page table is not on the hard drive. This is also in the RAM, right, inside the RAM. An operating system knows the address of this page table. An operating system will tell that address to MMU that if you want to find a page table for this process, go to this location and you will find it over there. So that's another important concept you should know. Now, as you can see that it's important for operating system to perform better, and it's important for operating system to give the required information to CPU on time. If this is not happening, then operating system might not perform well, right? Now, what is happening right now? What is happening right now is, as I told you over here, is if CPU is looking for a specific page, what CPU has to do? So let's say we have an operating system and CPU said that I'm looking for page 4. Let's assume that these are the pages for page 4. I'm looking for, so CPU says that I'm looking for page 2 of process 4. So it asks this request from operating, and CPU will say, where can I find this? So what operating system will do is, operating system will go to MMU, memory management unit, and it will ask for this information. So what happens now is, memory management unit will go, since memory management unit is managing a lot of page tables for each process, what it will do is, it will first of all go and search for the page table of P4 in the RAM. Right, it will go and search for P4's page table in the RAM. This information will be provided back to operating system, and operating system will provide this information to CPU, telling him that first of all, go and fetch for me the page table for P4. So CPU will go and fetch page 4 page table for operating system. So operating system will get that, give this back to memory management unit, and memory management unit from this page table will find the frame number where this page 2 is stored, right? And then it will give this information back to operating system. Operating system will give this back information to CPU, and CPU will go and fetch that page 2 from frame number 1. Now if you see, CPU has to do two things now. CPU has to first of all bring page tables for OS and memory management unit, and once the information for that specific page is available, it will go back to the main memory and fetch that page from that frame number as well. So operating system, so CPU had to do two things, right? Once get the page table, second get the page number, right? Which decreases the performance, right? So CPU had to do two things, although it asked for one thing and it says bring me this first and then I will give you this information, which will reduce the overall performance of the system. So we need to increase this paging process. So how to increase this paging process? We have several ways of doing that. One of them is translation look-aside buffer, right? Translation look-aside buffer. What this does is, it's a hardware. Translation look-aside buffer is basically a register. It's a hardware normally called as associative memory as well. Now in this case what it does is, it maps some virtual addresses to physical addresses. It maps the virtual addresses to physical addresses or logical addresses to the physical addresses. And normally this register is inside MMU. What happens over here is, it actually, now let me show you this over here. So what is happening over here, it contains this buffer, or this register actually contains this information of the virtual pages, and those are mapped to those specific frames, right? And this is a hardware. This is a hardware. So now if CPU is looking for a page 140 inside the frame, looking for page number 140 that is placed in frame number this one, CPU will request that to OS. OS will go to MMU, and MMU contains translation look-aside buffer TLB, which is a hardware where this information is stored. Now instead of MMU asking CPU to go and fetch me the page table first and then I will give you this information, based on this information placed over here, based on this information which is placed in a hardware instead of the main memory. This information is stored inside TLB, which is a register. Now if CPU is asking for virtual page number 140, instead of operating system asking CPU bring me the page table first, it will go to MMU containing the TLB, and TLB contains this information. This information of page frame will be given back to the operating system, and operating system will give this back information to the CPU, and CPU will go to the memory at location number 31, and fetch from there page number 140, right? So one cycle of CPU of fetching that page table has been reduced now, right? So it doesn't have to fetch that page table from the memory first, give it back to operating system, MMU, and get that information. This whole information is now available in TLB, translation leukocyte buffer. And since it's a register, it's very fast. It's very fast, right? So this is how we can speed up our paging using translation leukocyte buffer, right? Now, what is happening in translation leukocyte buffer? Now, sometimes, now of course, I mean, this TLB has limited space as well, right? It doesn't have enough space. It has space less than even the main memory because it's a register, although it's very fast, but it has less space. So these entries cannot stay here forever. These entries will keep on replacing each other, right? So it contains the information of, normally it contains the information of most accessed or recently accessed pages, right? Recently accessed pages. So all the pages that are being recently accessed, they have entries over here, right? So they have the entries over here. Now, so if these entries are here, CPU can easily fetch that information from TLB using MMU. It doesn't have to go to memory, fetch the translate page table first, right? So these entries are not permanent, and these entries will keep on changing themselves based on what is happening over here, what CPU is requesting. So CPU requested 140, so this entry will stay here. Next time, for example, let's assume maybe 950. So CPU is looking for 950. Page number 950, and 950 is not here, right? 950 is not here. In that case, what will happen is, same thing will happen. So what will happen is, CPU will ask operating system, I need 950, it will go to MMU. MMU will look into this TLB, do I have an entry of 950? Now it will not find this entry in the 950. This is called a miss, right? A miss. Okay, this is called a miss. We were looking for this information in the translation leukocyte buffer and we couldn't find this information, so this is called a miss. In that case, what will happen is MMU will tell operating system, I do not have that information in TLB. So in that case, operating system will ask CPU, okay, go and fetch for me this page table first, all right, because I couldn't find that information here. Go for fetch for me a page table, the whole page table for the process, right? It will fetch that page table, give it to operating system will give that to MMU will find that corresponding frame from here and give it back to operating system, and operating system will give that to CPU, and CPU will go to that frame and fetch 950, right? So it will have it, in that case it has to do that. So in case of miss, when MMU got page table from the operating system and CPU, what it does is it will place another entry of 950 over here as well, right? So it says that operating system was looking for this page, so let me better have an entry for this. So next time operating system looks for 950, it will go and fetch that information from TLB. It doesn't have to go there. So next time, let's assume operating system looks for 950 again. So it will go here, operating system will go to MMU and ask for 950. 950 entry is now available over here. This is called a hit. It means that this entry was available and this information will be provided over here, right? So this is how paging can be can be increased. The speed of paging can be increased using translation leukocyte buffer, right? So now there is a concept called soft miss and hard miss. Now we know what a miss is, we know what a hit is. So if a page is in the TLB, it is called a TLB hit, right? We know this. If page is not there, it's called a TLB miss. Now there are two other concepts of miss. One is called soft miss and one is called hard miss. Soft miss means if a page is not in TLB, as I said, this 950 was first not in TLB, It was not in TLB, but it was available in the RAM. It was available in the RAM because of the page table, right? It was available in the RAM because of the page table, right? Now this is called a soft miss. If this information was not even available inside our RAM, this is called a hard miss. If a page table was not available in the TLB and it's not available in the RAM as well, then it is called a hard miss, right? I would ask you guys to do a little bit more research on soft miss and hard miss. I will leave it over here. There is another concept which I have not explained over here, but I will quickly go through that, and I would like you guys to go on the internet and search for it and do some more research on that. So instead of page tables, sometimes what TLB is maintaining over here is TLB, for example, let me see, let's say we are looking for page number 55, page number 55. So CPU looks for this information in MMU, and MMU looks for this information in TLB. This information is not available over here, right? So MMU will ask CPU to find that information of 55, page number 55, inside the RAM, right, itself. So there are frames, so it will go and search for this information again. So sometimes MMU might ask operating system to not fetch the page table, instead go and find that information inside the RAM. If you find this page in the RAM, you can use it and tell me that you found it. If you didn't find that information, then you can ask operating system to fetch that information from the hard drive for you, right? So this is another concept of hard and soft miss, and I want you guys to look into it. All right, I'm going to move forward. This is going to be the last slide. So what we have over here is called a page table for large memories, and it's called a multi-level page table. Now we are saying that the RAM actually contains the pages, and it contains the page table as well, right? So let's assume that our frame, so this is frame number 1, and this is, let's assume, frame number 10, right? So we have frames. So let's assume the size of the frame is 4 KB, right? Let's assume the size of each frame is 4 KB. Now if you know that the page table is inside this, now page table also has some size, right? Some size. Now let's assume that a page table is generated for a process that has a size of 6 KB. Let's call it 8 KB. Now this cannot accommodate here because the frame size is 4 KB. What do we do in that case? We cannot place the page table inside this RAM. What do we do in that case? In that case, what we have to do is we have to divide this page table into further pages. So this page table will now be divided into 2 sections: page table 1, PT1, and PT2, right? Each one has 4 KB of size, 4K size, right? And this is our page table, the original page table. Now why we are doing this? Because our page table size is more than the size of the frame inside the RAM, right? So in this case, this page table cannot move into this RAM, right? So our frames cannot accommodate this page table because the size of the page table is more than the size of the frame. In that case, what we do is, in order to solve this problem, we divide our page table into further page tables. So we have page table 1 and page table 2. The size of page table 1 is 4K, and size of page table 2 is 4K. Now we can accommodate this page table. So PT1 can be accommodated here and PT2 can be accommodated here, right? And now we can work on our processes just like we did before. So what is happening over here? We are using multi-level page table. So we have a page table first. This is the first level of the page table, and when CPU looks for the page table, it will further have to go inside the RAM and look for that particular page table. And once it finds that page table, it will give that to MMU, and MMU will go and fetch the frame numbers for the CPU. So there are multi-level page table, which means that first level is the page table level, where page table itself is divided into 2 pages, and then those page tables are then placed into the frames and so on, right? This is what is happening over here. So this is the top level page table. So this is a page table which is further divided into multiple pages. So page table 1 and page table 2. So page table 1 and page table 2 are placed inside the RAM in different places, and so on. So this is the level 1 and this is level 2, right? So it might have multiple pages, not only 2 pages, it can be 15 or 100 page tables, right? They are divided based on their size of the frames. So such situations might occur. In that case, multi-level page tables are used, and these are normally used for large memories. Large memories means when the page table size is more than the frame size, right? So in that case, if we have a problem like that, we can have nested page frames, page tables, and nested page tables or multi-level page tables can be solved using this scenario, right? I hope you guys understand. So this is the theoretical part of this lecture. So what I'm gonna do is I want to quickly solve for you one exercise of memory management, and we want to see how it works, right? So what I'm gonna do is I'm gonna show you quickly one exercise, how it works, and what questions can you solve. Let's see, for example, in exam, if you get a question like this, how do you solve a question for that? So for example, in your exam you might have a question something like this, just saying that virtual address space is location of a program. So this is just some information of what is a frame, what is a pages, and what you have to do is please illustrate the steps required to map a virtual address, a logical address, which is this one, to a physical address in the memory using the page table MMU figure, right? So this is our address space. I've shown you this figure during the lecture also, right? So this is virtual memory space and this is main memory space, right? This is main memory space. So these are all frames and these are all pages, right? Now we have this logical address which is somewhere here, a logical address. So it will 36864 36, it's somewhere here. So this one, number 5. So it falls in this range. So we are talking about this address. We want to see where this address is stored in the RAM, right? So that we can go, and so this is our page number, and we are going to translate this into our frame numbers, right? And frame numbers will fetch our pages back to us, right? So let's see how this works. So we have our logical address and we have to convert that logical address into physical address, and this is how MMU works, and let's do that. So we assume that this is the page table. So this is the page table. So it has some addresses 0 to 15. So since we are talking about 0 to 15, we can have maximum of 3 bytes, 3 bits, right? Because 15 can be represented in maximum 3 bits. We cannot increase the bits. And these are absent and present bits. This is actually a figure of a page table where each page table entry is over there for you, and it says 0 and 1 if there was a page fault or not. But I don't want you guys to look into it. I just want to tell you that this is a page table entry, right? And these are our this is our page table. So these are the entries, and this is how we are going to move to our physical address. So we will come back to it. Let's see what steps do we require. So if you are given a logical address or a virtual address, how do you convert that into a physical address? This is what we want, and going to that physical address, we want to fetch that page, right? This is what we want. First step is to convert that virtual address into 16-bit binary number, right? So we had this number 36864. We need to convert this into binary number first. We know how to convert it into binary. So this is where our binary number is for this number, right? This is the first step. Second step is remove the first 4 digits and change it to decimal, right? Remove the first 4 digits. So what are the first 4 digits? 1001, and that becomes 9. So take those first 4 digits and convert them into decimal, right? These first 4 digits are 1001. 1001, that is our 9 in decimal number, right? In decimal number, this is our 9, right? Now why only 4 digits? Because this is based on this page table. It might be 5 digits, it might be 10 digits, but just to keep it simple, this is a screenshot I have taken from the book, and just because I didn't want to create all the page table myself, so I have this page table already available, so that's why I have created this example based on this. So we take first 4 digits because the entries in our page table are like this. So 3 digits and 1 digit for absent and present bit, right? So what we are going to do over here is we are going to take first 4 digits, convert that into decimal. So we trim that, keep the offset as it is. So if you see this one, what is happening over here is the first 4 is the page number and the rest one is our offset. If I go back and show you that, where was it? This one. So there is a page number in the logical address and there is an offset. So first 4 digits as per this diagram, first 4 digits are for the page number. Rest of the 12 digits are the offset. So we keep the offset as it is. If you remember here, we keep the offset as it is. We take the page number and try to see where it maps to the frame number. So we took the first 4 digits, that convert that back to 9, and we go to our page table and go to entry number 9. What is entry number 9? 101, right? So entry number 9 is 101. So we are going to replace these 4 digits by whatever we got in the table at 9 place, right? So this is our offset, right? We keep this aside and we are keeping this aside. We just replace 9 by 101. Why? Because at page number 9 we found the entry 101. This is the frame number. This is my frame number 101. So I'm gonna take this 101 and the offset and I end up getting this value, right? So at location number 9 I got 101 and I have again appended that 101 with my offset, which was the offset which I kept aside when I started, right? Now I have this number and I convert this number into this, right? So I will convert this binary number back to the decimal number, which gives me 20480. Now since I have address ranges, over here, so so over here in this example I am having an address range, so 0k to 4k, 4k to 8k. I do not have absolute addresses over here, so this is not 4k, this is not 8k, this is not 12k. I have ranges, so it means that any address between 0k and 4k will fall here, any address from 4k to 8k will fall here, and so for the frame numbers, right? So I have got an address, I've got a number in decimal which is 20480. Now since these are in kilobits, in order to convert this into kilo, I will divide it by 1024, right? I will divide this number by 1024. I end up getting 20k. So 20k, I have to find where that 20k is. So 20k is over here, right? Over here. So I end up finding this number over here, right? So this is what, sorry, over here, this one, 20k is over here, right? So this is basically 16k to 19k something, but over here this is actually 20k to 24k. This is not accurate, but this is how we map. So if you see, based on this diagram as well, 5 is actually mapped to this location. So if you remember, 36864 is somewhere this location, right? Because we are going now, now this is not very accurate because obviously these are ranges, that's why we had a problem over here. But obviously these ranges are not going to be like this. Memory addresses are very absolute. They are absolute values for each address space, so that's why we end up over here. So 5 is mapped over here. Whatever value is over here we get back for our CPU, right? So this is how you convert your physical logical addresses or virtual addresses into your physical addresses, right? So what I want you guys to do is try to rewind this video instead of me explaining again. You have a liberty of rewinding this video and make me do this again for you. So try to do that, and what you can do is try to pick another address from here. For example, pick 7 from here and see if when you take all those steps, does it map properly here or not for you, right? Try to take another one and try to see if it maps over there or not, right? Try to do these things and see if it works for you or not, right? And this is a very important task. Try to do this for a couple of other other memory addresses over here and see if it works for you or not, right? It should work for you. So this is what exercise we have for today. We are not going to have any programming exercise today. I'm gonna stop over here because uh, this is already a big lecture and we have covered so many different important things in today's lecture, and there is more to come. That's why I wanted to split this lecture into two halves, and we are going to talk about memory management 2 in coming lectures. So we are going to talk about some more algorithms. So I'm gonna stop here. I would expect you guys, just like one of the lectures I said previously, try to maybe go through this video twice if you have time to get better understanding of what is going on. And as I always say, if you still not able to understand or grasp any concept what I told you over here, please arrange a session with me and I would love to explain these concepts to you once again. It is very normal if you don't understand anything from here. It's absolutely normal. I remember when I started understanding this, it took me a couple of times to go through this and then I was able to grasp these concepts. So it's absolutely fine if you don't understand it first time, try to go through the videos once again. If you still don't understand, let's meet up during my virtual office hours, or if you have any other time which suits you, just let me know through the email and we can try to arrange a session for you. But try to understand these concepts. These are important for your overall understanding, and these are also important for you for your exams, as far as your exams are concerned. I'm going to place this file on Blackboard as well, so you can grab that from Blackboard. And I'm going to stop here. That's pretty much it for today's lecture. I'm going to see you in the next lecture. If you have any questions, please drop me an email. Have a nice day. Have a nice week. Bye bye.